to my channel. Today we're gonna work on the question, all path from source lead to destination. The question states, given the edges of a directed graph where edges AB indicates there's an edge between nodes AB, and we have two nodes, source and destination, determine whether or not all paths starting from source eventually end at destination. 1. At least one path exists from the source node to the destination node. 2. If there's a path existing from source node to a node with no outgoing edges, then that node is equal to destination. And 3. The number of possible paths from source to destination is a finite number. Return true if and only if all roads from source lead to destination. Let's look at the examples. So example 1, source 0, destination 2. We can see that it's false because source can go to 2 or 1, and our destination node is 2. So it's possible to reach and get stuck on both node 1 and node 2. Let's look at the second one, source 0, destination 3, and it's false because it can go to here 3, and it can also get stuck here in a loop. Let's look at example 3, source 0 and destination 3. So source can go this way to 3 and source can go this way to 3. So all possible path leads to 3, which should return true. And to solve this, we can use a coloring scheme, DFS. Let me define the coloring scheme that I'm gonna use. I'm gonna use white, gray, and black, but white is only gonna be, I'm gonna tell you what each means, but I actually won't be using white because white is nodes that we haven't visited yet. So it'll be, all nodes will be initialized as white, and the initial states of node is white, and gray is when we are processing this node, meaning we've visited it, but we haven't gone through all of its children, all of its outgoing edges yet. And black is when we finished visiting this node plus its outgoing edges. So basically, when we're traversing a graph, if we do encounter a gray again, that means we visited this node before, but we encountering it again means there's a cycle, right? So that means there's a cycle. But if when we go through our nodes and we encounter a black, that means this node is already completed and it's done, and there's no cycle, which is dead. So the reason why we're using a coloring scheme, I can show you an example here. It's to catch an edge case. So basically, if you look here, we can see 1 goes to 2, goes to 4, and 2 and 4 turns to black nodes, and then 1 goes to 3, and when 3 goes to 4 again, 4 is already visited, and this is not a cycle, even though it looks like a cycle. This is actually just a cross edge. So that's why if we use a visited array, it wouldn't help us detect the presence of this type of cycles. And let's start writing the code. So I'm gonna form my adjacency list using default dictionary. So I'm just gonna import the default dictionary right now. And then I'll define the gray and black here. So first I'm gonna form my adjacency list. So I can do something like adjacency list equals, let me write a function to define build adjacency list self, and then it's gonna take in edges. So I'm gonna call it as build adjacency list. And then I'm gonna pass in edges. So for source, wait, I'm gonna define it first. Adjacency list equals default dictionary of list, and then for source destination in edges, we can append it to our adjacency list. So adjacency list source dot append destination, and we're only gonna append it one way because this is a directed graph. We don't have to do it back and forth. And finally, we can return our adjacency list, and it will just span it here. I'm writing it this way for it to be more object oriented. And then now we can write our DFS. So DFS, we can take in our adjacency list, a node which is initially going to be the source node, and then the destination, and also we can have a color state to record our current color state. And initially we can return this as self DFS, and then adjacency list, source destination, and then color state will be initialized as white. And because everything is unvisited in the beginning, let's just assume white is none, so it's haven't been visited yet, and then we span it to the size of the graph, which is n. Now let's start writing the DFS. The DFS is going to we have to do base checks for DFS. So there's two things we're checking here. The first thing is whether there's a cycle, and if there is, we immediately return false. We can check whether there is or is not a cycle by going through the coloring scheme, so showing our DFS. And when we visit a node that's already been visited, then we can just, and it's gray, then we just return false. And the second thing we need to check for is whether a destination node. A destination node is defined as a node with no outgoing edges, and then whether all destination nodes equal to the given destination nodes, right? And if it doesn't equal, then we can automatically return true or false. So let's start with these two cases. The first one, let's check for cycle. We can check if color state of the node if the color state of the node does not equal none. So if it does not equal none, then it means it's either gray or black. It has been visited before, but we don't know whether it's gray or black. And then if we can return true if it equals black. So basically, return color state node equals black. Solution black. And the second one, this is to check for cycles. And the second one is going to be checking if we've reached a destination node. So we can check by doing the length of adjacency list of the node equals 0. That means when there's no outgoing edges for that node, it's a destination node. And when it's 0, we can return true if the node equals to the destination here that's passed in. And then if it does not equal, it will automatically return false. So those are our two base case checks, and if we encounter any of this, we will just short circuit and our program by returning false. So now let's actually visit our node. So color state, we can change it to gray now of the node equals to solution dot gray, because now we've officially visited this node, but it's gray because we haven't visited all its children yet. So let's go through the neighbor for neighbor and adjacency list node, and then if not DFS, adjacency self.dfs adjacency list neighbor destination, and then color state. So if it returns false in these two, it automatically return false here, then we can immediately return false. It will short circuit and return false, and otherwise if we go through this whole thing without returning false, that means everything past these two base cases, there's no cycles, and all nodes, all destination nodes equals to our given destination, which is right. So now we can successfully assign this as visited, so officially label it as black. And finally, if we go through everything, we can just return true at the very end. Yeah, so this is our algorithm. Let me see if it goes through. It's been accepted. So let me know if you have any questions, and thank you so much for watching.